Hey, what's up guys? This is Audie from ShastryNation, and today we're going to be talking about homeostasis. Alright, so now that you're back from the intro, I guess we can go ahead and write it down. Alright, so homeostasis. Oh, that is really thick. I think like 60%. Yeah, okay. So homeostasis. Oh, that's better. Okay. So I guess okay, so in this video we're going to talk about like osmoregulation. Oh, I shouldn't have wrote that. Never mind. Okay. And thermoregulation. Right? So osmoregulation and thermoregulation. And so thermoregulation, you should probably, be able to figure out what that is. It's basically just the regulation of heat, and then osmoregulation is the regulation of water. Sorry, I'm trying to fix stuff and also talk at the same time. So, anyways, I guess we can go ahead and get started. Okay, so what is, I guess, homeostasis? So homeostasis is going to be the thing like how the body or the organism, how the body regulates certain factors or stimuluses or stimuli, I guess. Yeah, stimuli. Stimuli. Okay, so what do I mean by this? Okay, so for example, I guess I can use a human example. When it's really hot outside, like it is right now, we tend to sweat to cool our bodies down. So that's one of the things that we do in order to cool down and try to bring that temperature down to a certain level, because all of the mainly the reason for homeostasis is it's because like all of the enzymes in our bodies need to actually be in a certain point, like we've talked about in a previous video. Sorry, I have to move the mic. Okay, but it's because certain like enzymes need certain environments in order to work in the best possible way, and not become denatured basically. So that's why we need that. Now, the exact point at which that stimulus or environmental factor or that thing, I guess, should be kept at is called the set point. Okay, so I'm gonna go ahead and say it again. So a set point is basically where the for example, if the set point was I don't know, 96 degrees or something like that. If the set point for us, for human beings, was 96 degrees, that would be like 96 degrees, and the body will try to keep it in that range, or the range would be called the normal range. So that range will be called the normal range, and so the normal range is going to be basically, it's going to be like a range of temperature that it's fine in. You know what I mean? So like, I don't know if you guys know how a pool works, and with all the chemicals and stuff in pools, but in order for the pool to be open, you need to have it. You need to have the pH, for instance, in this certain range. So like the pH should be between 7.1 and 7.8 or something like that, for example. And if it goes out of that range, you'll have to close down the pool. So basically, the same thing happens in the body. If the temperature, for example, goes out of that range, we'll start to sweat. If it goes hotter, and then if it goes colder, we'll start to shiver, and change our body position to conserve heat and things like that. Okay, yeah, so that's basically what a normal range is. Now, also, I guess there's two different types of, two different ways, I guess, you can deal with an issue like this. So the two different ways, I guess I'll write it in a different color. Okay, so there we have our regulators. So we have regulators, and we have conformers. Okay, so regulators are going to be basically, they're like us. So for example, like with regard to heat, again, I'm going to use the heat example. Regulators like us would try to get rid of that heat, and try to cool ourselves down when it gets too hot. So these are going to be like, they're going to try to control where that variable, heat, the external factor or whatever it's in. So it's going to try to control it. Tries to control, I guess, the factor. And then conformers are basically the opposite, okay? They're just going to be like, okay, it'll be like, for example, if we took osmoregulation or water regulation, starfish are, osmoconformers, and so basically they will just, they'll conform to whatever is happening in the environment. So for example, I guess the popular term for this, it would be cold-blooded animals and then warm-blooded animals. Warm-blooded would be regulators, and cold-blooded would be, like your reptiles and things like that will, try to get outside assistance to actually maintain their body heat. So, for example, like a lizard or something like that will try to, stay in the shade, as much as it can, because, if it goes out, or like a worm or something like that, it will try to stay in the shade or, underground or something like that as much as it can, because, if it goes outside, it has no way to actually regulate that heat, and it'll end up dying. Basically, that's about it. So this thing, I guess I'll just write down like, it doesn't expend. Okay, so that's a better one. The regulators expend energy, so they expend energy to control the factor. Control the I guess maintain homeostasis. Okay. And then the conformers don't expend. Don't expend energy to maintain homeostasis. I'm not gonna write that. You guys get the point, I guess. Okay. So now one of the things is with this, not all animals fall into one category. There's a lot of, mix and match. For some things, for some animals, they might be regulators for osmoregulate, for water and solute concentrations and stuff like that, but, conformers for temperature. And, the opposite goes for some other animals and things like that. So don't think of it as, okay, hey, it's a reptile, it's going to be a conformer for every single stimulus or, I guess, factor of homeostasis. That's not true. It always changes. For certain things, it'll try to, make its environment better, so it can, I guess, sustain life. And just don't make the mistake of thinking that certain animals fit into one of these categories, because it's a common mistake. It's one of those things that people do. I don't know. Okay, so then all of this stuff is going to be controlled by. So it's going to be controlled. Okay, I'm just going to write that again. And there we go. Good. controlled by it's going to be controlled by feedback loops. Okay, so if you remember from that video where we talked about where we talked about how I guess how enzymes and things like that, not enzymes, but like, like DNA and expression and regulation, things like that. When we talked about regulation of DNA and genes, if you remember that video, if you haven't watched that video, I would go and watch it. But if you remember from that video, you would remember that, a lot of the genes that are controlled are going to be, that are regulated are going to be, expressed when it's needed. You know what I mean? So like, we're not going to make a gene, for example, for the lac operon model. We're not going to make a gene. We're not going to make enzymes for that consume lactose. Yeah. So we're not going to make lactase to consume lactose until we actually have lactose in our system. And that's when we actually go ahead and our cells in our body, or stomach cells, are going to go ahead and make those to consume that lactose. So basically, there's two types. So there's positive feedback loops and then negative feedback loops. Positive is going to amplify. Positive is going to amplify the stimulus. It's going to, I guess the stimulus, I can say stimulus. Okay. And then negative is obviously going to reduce the stimulus. Okay, so I'm only going to give you an example for one because, the other one you will understand, how that's going to work. But for positive feedback loops, for example, an example of that, I guess, would be, of apples or something like that. Basically, when an apple ripens, and it becomes, red, it'll actually release ethylene. If you remember what ethylene is, ethylene is the thing that will, it's basically the, chemical that will make fruits and basically all types of fruits ripen faster. So if you remember that one from the, the plant hormones video, if not, I would go and watch that too because it's pretty cool, I guess. It's not going to be used much, but hey, I would go and watch that one. In this video, at least, it's not going to be used, but it might be used in other videos. You never know. So I would go and watch that one. But anyways, once one apple ripens, it'll send send the ethylene chemical or molecule or whatever to different apples, and then those apples will send it to other apples, and then by the whole, and those will send it to more, and then more, and then more, and so it'll basically grow, geometrically. So it'll be like, okay, first you'll start out with one, and then let's say you get three, and then those three will get three, and then those three will get three, and then three, and then three, all the way up till whatever we get. So I guess exponentially or geometrically, I guess, works too. I don't know. I'm not. It's been a while since I've done that stuff. So yeah. That's basically about. That's the example of positive. So negative would be like the opposite of that. So for example, you'd have if we use the same example, you'd have a bunch of ripened apples, and then they'd go backwards. And so once one does that, it'll basically go backwards. But you can get the you have the idea to get the negative one. Okay, so I guess we can move on to our main big topic, which would be thermoregulation. thermoregulation. Okay, so this is the controlling of heat. So it's like I guess temperature regulation. Yeah. So temperature regulation. One of the things that we're going to talk about is the Q10 effect. I guess we can start out with that. I mean, it's not really important, but you know, it's still pretty cool to know, and you know, you should know it for the test and things like that. Okay, so basically the Q10 effect is, if you remember from the enzyme video that I did, and you know, if you remember from that video, when the temperature is actually increased, the enzyme will speed up its production, you know, because the temperature is increased. And so basically the Q10 effect is, it'll determine how much, you know, how much faster an enzyme will do, you know, if with a 10 degrees change. So for example, you know, let's say we change the degrees from 70 degrees Celsius to 80 degrees Celsius, and the I guess enzyme got, you know, 20 times faster. You know, so the enzyme got 20 times faster. You know, or yeah, let's just say it got 20 times faster. Okay, so basically the Q10 for that enzyme would be 20, would be equal to 20. So that's basically what that is. So for every 10 degrees, you know, it'll get 20 times faster. Basically, is what that's saying. Until, you know, obviously the graph will look like this with enzyme production. It'll go up and then it'll fall down. After some point, it can't, you know, it'll just get denatured because the bonds are gonna break off and things like that, and the shape will change. Okay, so now we did talk about regulators and conformers. Well, here they're called different things, okay, but they're the same. So the same idea. So these are called ectotherms, and then we have endotherms. And so a cool way to remember this, I guess, I don't know, it works for me, but ecto, you know, ecto means like outside, you know what I mean? So like, you know, always when there's, you have a feeling like ecto means like outside, and so outside, you know, so if ecto is outside, so ectotherms would be, you know, conformers. So these are basically conformers. And then endotherms, you know, endotherms would be like endo meaning inside, so they're going to be trying to regulate the temperature, so regulators. And so basically it's the same. It's not any different for these guys. It's the same definition or anything. So I'm not going to go ahead. I'm going to go ahead and move on because we already went over that. And I'll move on to something else. Okay. So we might actually even run out of room on this one because there's a lot of stuff. Okay, so how is heat actually going to be controlled? So how is heat going to be controlled? I say heat, but you know, cold really isn't a thing. It's not scientifically there. Cold is the feeling of cold is lack of heat, you know, and so heat is like the measure of energy, right? So cold, it's not measure of anything. There's I mean, we obviously use cold for a lot of things, but there, you know, whenever in science, you know, whenever you're writing something or anything like that, remember to say lack of heat, because it's not, something's not cold, it's just lacking heat, because there, you know, really in science there's no such thing as cold. So I don't know, it's just something that I had to mention. Okay, so I guess we can go ahead and get started. So there's some things with so there's insulation, and so this is going to be like fat and you know, muscles and things like that. Fat, basically, insulation, you know, just like you have insulation in your house, basically, you know, it's the same thing. You have vasodilation. Okay, vasodilation, basically what happens is that, you know, so I guess I'll put down my pen and I'll actually talk about this. Alright, so vasodilation is, there's vasodilation, and I guess I'll write the other one too, vasoconstriction. So, oh, my bad. Okay, so my bad. Vasodilation. And vasoconstriction. Okay, so vasodilation and vasoconstriction. So vasodilation is going to be like the expanding of the arteries and things like that to let heat or like the blood come to the top of the skin, you know, and so actually reach the epithelial cells of the skin, so heat will dissipate. So I guess I'll draw a hand or something like that. So it's just, actually, I could just trace my hand. So that's what I'll do. No, I don't know if that'll work. Okay, so I'll just draw a really poorly drawn hand, I guess. Hey, there's a hand. Okay, all right. Anyways, I guess I'll use red. Okay, so anyways, normally like the heat, you know, the blood vessels will go through like this, you know, and they'll go to the different hands and, you know, fingers and things like that, and all parts of the body. But when there's too much heat, okay, what the blood vessels will actually do, in order to get rid of that heat, is they're gonna actually go to the surface of the skin in all parts. So they're gonna go to the surface of the skin, and so this heat is going to, and you know, there's obviously gonna be sweat there, so the sweat will take up the heat and then go away. So it'll, you know, dissipate the heat basically. Okay, so basically that's what vasodilation is. Now, basically that's what happens, you know, and that's why, for example, you know, on a really hot day, when I guess if you go outside on a really hot day and you see someone walking, that's why their skin is completely red. Now, this is more noticeable in certain people based on their skin color, and not so noticeable in other people because of their skin color. But, you know, if you're really hot, you can, next time you're, you know, really hot or really, really warm or something like that, your body will try to get rid of the heat, and so you know, everything, your whole body will be red trying to do that, trying to get rid of that heat. Okay, so I guess I'll use the same one, the same hand, because I don't want to draw one again, because I really don't like drawing. Okay, so vasoconstriction is like the opposite. All right, so whenever you're really, really cold, okay, you know, obviously you'll shiver and things like that, but, you know, your body's gonna also try to constrict the heat, okay? Now, every time blood goes to the outer extremities of your body, so like your hands, fingers, nose, ears, things like that, whenever the blood actually goes to those parts of the body, it loses heat. Okay. Now this is going into another thing, but anyways, for example, when it's really cold outside, okay, your body's not gonna want to get rid of heat, right? It's gonna try to contain heat. So basically, what it'll do, it'll instead of going to, like, you know, closer to the thing, so it'll go like that. Usually, it'll actually just go. It'll try to stay away from the outside. So it'll try to stay as much to the interior of the hand or whatever body part we're talking about, to not let that heat dissipate away and go away, because that heat is valuable to the body if it's freezing outside or things like that. Okay. Sorry. Okay. And then I guess we have so I don't really need to explain that, right? I don't need to write it down. Yeah, I won't write it down, because it's really difficult to write down I just have to explain it honestly, vasodilation, constriction. But once you understand the whole concept, it makes sense. Like what I just explained, it makes sense if you really understand it. Okay, and then so we have countercurrent heat exchange. Okay, and so this is when it's like really cold outside or there's a lack of heat outside, and your body will try to constrict the heat to the center of your body. All right, so basically, what happens here is, okay, so let's say you're outside, it's snowing, and you're really cold. You forgot to bring your jacket or something like that. It's snowing. It's like a blizzard. Okay, let's say you're outside. Okay, as you know, there you have, you have your veins and then you have your arteries and things like that. So the veins will actually bring it back to the heart or the center of the body. Okay, and then you'll have the actual arteries and other, things like that that'll take it to the to the actual cells and things like that. Okay, so basically what happens here is that, you'll have your blue cells, but it's not really a blue cell, it's more like a darkish red, but for our purposes this is fine. Okay, so oh my bad, this will go this way. Okay, and then you'll have your normal red cells with oxygenated red blood cells that'll go that way. And so basically what happens here is, I'll get a yellow color, when it's really cold outside, your body will try to constrict the heat to the center of your body, where it's needed. So for example, like your heart is the most important thing, and then your brain, and then since all of your major organs are in the center of your body, it's going to try to keep that heat to the center of the body. Okay, and so basically what's going to happen is that all this heat, this is going to be the blood going to the hand. For example, in this example, the blood going to the hand will be warm because it's going to be coming from the heart and it's going to be warm in the heart. Now, the blood going back is going to be cold because it's going to go here, and all the heat's going to basically dissipate away and then go here, right? Now, what happens is that if we go into this, what happens is that these arteries are going to run right by each other. So I guess I'll write it. Okay, so these arteries are going to go right by each other like this, and so basically the heat will diffuse across like this. It'll go across to that side of the thing, and it'll go back. So it'll go from this one to this one, and so the body will try to contain the heat in the center of the whole system, like your whole body. It'll try to contain the heat in your chest, and feed some to your brain and things like that. That's just a fail-safe method of trying to constrict, trying to stay alive in really cold or really harsh environments. That's basically what countercurrent heat exchange is. Okay. Now we also have now I'm not gonna go write something about that, but that's basically what it is. It's gonna change the heat or something like that. Okay, now also when it's really cold, you probably notice that you shiver. So okay, you shiver. Now I actually did a whiteboard video on this. I'll try to see if I can remember to link it. But you can probably find it in my on my channel. I actually did a whiteboard video on why we shiver. If you want a really quick 2-minute version of this whole thing, I would go and watch that because it's pretty cool. And I work really hard on those. Those take a really long time to make. Just trying to put everything together into perfect placement and things like that. It just takes really long. So I would go and watch that. Okay, so shivering is going to be, shivering, just go and watch the video. Honestly, I explained it pretty well, I think, in that video. But, I guess if you don't want to go and watch that video or click off this video, I'll go ahead and explain it to you, a brief version of it. Basically, when you shiver, you'll use ATP, and heat will be released by using ATP, and so your body will generate heat by doing that. Okay? This one's probably going to be my longest video. Yeah, I don't know. Okay, so back to countercurrent heat exchange. I forgot to mention something, but there's always those stories about frostbite. I don't know if you've heard of frostbite. You probably would have heard of frostbite, but anyways, that's because of countercurrent heat exchange, and things like that. Okay, so basically, your body's gonna get so cold, that even this countercurrent heat exchange, this thing right here, even this isn't good enough to maintain heat, because your body temperature is so low that the body will basically cut off blood supply to the outside, your to the points of your body that are farthest away from your heart. So your body really is trying to maintain as much of its heat as possible and try to make you live as long as possible by doing that. Now, obviously, you're gonna have to, amputate your whatever. Obviously, the people are gonna have to amputate their hands, fingers, things like that if they are stuck in that situation, because the dead cells will then cause the rest of your body to the cells in the rest of your body to die. Yeah. Okay, so here's another thing. So shivering, that's basically it. So I mean, if that wasn't good enough, I would just go and watch that video. Basically, it's a really good one. I think I worked really hard on it, and my sister actually helped me with the drawings, because this is the drawings that I make. So definitely need some help with that. Yeah, okay, so before we waste too much time talking about this stuff, we're almost done, alright? So we have, last up, we have Osmoregulation. Yay, last one. Okay, osmoregulation is just going to be like the regulation of water, basically. And so, we do this too. Water and solute, sorry. So it's the regulation of H2O slash solute. So solute, by solute I mean like salt, various metals, things like that. Anything that is a solute, and that's basically everything in water, because water is a universal solvent. Okay. So basically, any solute is going to, throw off the whole balance of things. So now, for example, let's say, basically, water is needed by your body for many different reasons, but one of the reasons is to get rid of waste. And so, let's say, for example, you don't drink too much water, okay, for a day, and you have, you sweat excessively, you don't drink a lot of water, and things like that. But your body still needs to get rid of a lot of waste. Okay. Now, that's why when you pee, your pee will be completely like darkish yellow. That's because the concentration of waste is going to be higher than the concentration of water. Now, obviously, it needs a little bit of water to actually get rid of it, but the solute, there's going to be more solute than water. Now, for example, on the other side of the token, I guess on the other side of the whole situation, you'll have let's say you drank too much water, okay, and you didn't sweat, you didn't lose a lot of water and things like that. Your water will be completely almost white, not white but clear. It'll be almost clear, your pee. And so that's because your body's trying to come back to that set point, like we talked about before. That set point by getting rid of as much water as it can. Now it's also going to flush out some solute, but the solute concentration is going to be way lower than the water concentration. Basically, that's about it. Okay. So that's that. And then for this we have two different types too. So we have osmoregulators. And then osmoconformers. Okay, osmoregulators, osmoconformers. Same thing as what we talked about before. so not something too different here. All right. Okay, so let's see. Okay, now let's talk about saltwater and freshwater, like fish and stuff like that. Animals and organisms in freshwater and saltwater based ecosystems. So in saltwater ecosystems, So in saltwater ecosystems, so for example, let's take a fish. Okay. So the fish will try to it'll drink in all the salt water. Okay. And then it'll try to, like, get rid of that salt, okay? Because there's a lot of salt. It doesn't want all that salt. That salt is just going to, it's basically gonna, cause a high to low, high to low, like diffusion, and so it'll basically diffuse all the water out of its cells. That's why you don't actually feed plants salt water, because the roots will actually lose water. The plant will lose water rather than keeping water. So that's that. Okay. So salt water will try to get rid of solute. Okay, and then freshwater will do the opposite. Sorry, I'm just trying to finish this out because I think it's almost an hour now. Pretty sure. So this will just try to get rid of as much water as possible. So try to get rid of H2O. Okay. And I guess with that, we're good with this. Yeah. All right, so we're all done. Basically, just know this stuff that I talked about for osmoregulation. Know what homeostasis is, what regulators and conformers are, and then how it's controlled, positive and negative feedback loops, things like that. Know about thermoregulation a lot, and then, you'll learn about basal metabolic rates and things like that later, but that's going to be completely dependent on that. This is some cool stuff, actually, for me at least, because I want to be a doctor, but, I don't know I certainly find this vasodilation, insulation, vasoconstriction, things like that, pretty interesting. So, it's just good to know, and you probably won't see it on a test, but you might see it on a test. So just know it, and it, that's about it. I can't really say any much more about it. It's really interesting, I guess. Now we did do a case study regarding homeostasis. And I'll try to again see if I can link it below. It's a pretty cool case study. So if you want to go and do that, I know. I don't know. I always have fun with the case studies. I don't know why. I always did better on the case studies than the actual tests. I don't know. I guess I guess I'm just a creative thinker or something like that. I could figure out issues and things like that. I don't know. Whatever. I guess I just went on a mini, not rant, but just talk. Anyways, yeah, that's basically all you really need to know. Basically what I just said is everything. You need to know everything. But this is like the bare minimum of what I've covered, in this. Okay. So there's way more, regulation. There's regulation for everything, right? I guess this is it. I mean, really, there's a lot of stuff that I needed to cover that I should have covered or could have covered. I guess could have covered would have been better. Would it be a better word to say? But this is like the bare minimum. So just know all of it. It's not really that much information. It's maybe a few definitions here and there, but it's a lot of concepts that you need to understand, and so you need to also be able to apply it to certain situations, things like that. That's what they'll do on the AP test. They'll give you a certain situation, and they'll ask you like, hey, how would you for example, like they'll give you like it'll basically be like a case study, but it will be in multiple choice format. So our case study was for this was some guy went to a desert, got lost in the desert, and then he ran out of heat. He threw away his cap, things like that. He was red all over and things like that. He slowly started to sweat out all of his water, and he fainted. Then they obviously found him, things like that, and they're like, okay, why did this, why did he faint, or why was his skin red, and you would answer that, okay, his skin was red because of vasodilation, and things like that. So it's pretty cool, to actually do that. I'll try to see if I can link it down below, but you can probably find it yourself too. So I would suggest right after watching this video to go ahead and do some case study, or ask your teacher to have you do a case study. If your teacher is not gonna, hasn't already have it planned, he or she probably already has it planned. But it's a pretty cool thing to actually apply what you've learned in an actual situation. I don't know, I've always liked that stuff, so I don't know, that's probably just me. Alright, that's about it. And I guess I can end the video right now. And I will see you guys in the next one.